Welcome to the Greek Ship Corrosion channel. My name is احتشام زاده. I'm a researcher in the field of corrosion and protection of materials. Chapter 8, Section 4, Electrochemical Impedance Spectroscopy. In this video, advantages and limitations of EIS method respect to DC methods in corrosion studies, 2. EIS test method, and 3. An introduction to data presentation formats in EIS. Nyquist, Col, and Bode plots are discussed. Advantages of EIS method respect to DC methods in corrosion studies. 1. The primary advantages of electrochemical impedance spectroscopy over direct current DC methods in corrosion studies include its ability to rapidly characterize complex electrochemical systems across a wide frequency range, usually from 10 raised to 5 to 10 raised to -3 Hz, in order to provide full information on the corrosion process and cell performance. 2. EIS provides detailed insight into the corrosion mechanisms and allows for the evaluation of the kinetics of charge transfer and mass transport processes. 3. Additionally, EIS can differentiate between different corrosion processes and is less influenced by potential transient effects, making it a powerful tool for studying the stability and performance of protective coatings and materials in corrosive environments. Limitations of EIS method respect to DC methods in corrosion studies. One key limitation is that EIS can sometimes provide insufficient data at low frequencies, which may not accurately reflect corrosion processes or protective properties, particularly for coatings. 2. Additionally, EIS might be more complex and require careful interpretation of results, whereas DC methods tend to be simpler, cheaper, and easier to perform, although they may not offer comprehensive insights into corrosion phenomena. 3. Furthermore, EIS is more sensitive to environmental conditions and may not be as effective in certain media conditions where DC methods function better. It's important to consider these limitations in the context of specific applications and to verify critical information when evaluating corrosion studies. EIS test method. This method normally involves application of time-varying small potential excursions about corrosion potential, or ECOR, and measurement of A. External current, B. System impedance, Z, and C. Impedance phase angle, delta, the phase angle between the impedance and the applied potential. It should be noted that external current, measurable externally, is the difference in the oxidation and reduction current at the interface. Neither of each can be directly measured. External current, or external current density of oxidation of the metal, and current density of reduction of the metal. For positive overpotential, where eta CT or charge transfer overpotential is greater than 0, external current density is equal to the difference in the oxidation current density of the metal and the reduction current density of the metal, or oxidation current density of the metal is equal to the sum of external current density plus the reduction current density of the metal. Data presentation formats in EIS. In electrochemical impedance spectroscopy, data is typically presented in two standard formats: Nyquist plots and Bode plots. Nyquist plot and Bode plot. Omega going toward infinity in the left side, and omega going toward 0 at the right side. In Bode plots, magnitude of the impedance versus the frequency and phase angle versus the frequency, which is called Bode-Phase. Complex plane or Nyquist plot. EIS data often are plotted in the complex plane as -z double prime j axis versus z prime. It is instructive to obtain a relationship between Z double prime and Z prime by use of the related equations and elimination of omega. The dimensions of the impedance are electrical resistance times specimen area, for example, ohms square meters, and is normalized with respect to specimen area. The dimension of impedance is also expressed in ohms, as it combines both resistance, the real part of impedance, denoted as R, and reactance, the imaginary part of impedance, denoted as X, into a single value that can vary with frequency, as shown on the next slide. What's Corrosion plot? The Corrosion plot and the Nyquist plot are indeed related and can be considered similar in the context of electrochemical impedance spectroscopy. Both plots are used to represent complex impedance data. However, they emphasize different aspects. The Corrosion plot is particularly effective for visualizing the distribution of relaxation times, whereas the Nyquist plot focuses on the imaginary and real parts of the impedance. Relaxation time in EIS. In electrochemical impedance spectroscopy, relaxation time refers to the time constant associated with processes occurring within the system. Relaxation time in electrochemical impedance spectroscopy is commonly analyzed using a method called distribution of relaxation time (DRT), which converts impedance data as a function of frequency into a distribution of time constants. This technique helps in understanding the dynamic behavior of the system under study. Dynamic response theory can be applied to convert impedance data into a distribution of these time constants. By interpreting the frequency-dependent impedance data, researchers can gain insights into the underlying physical processes. These figures show an example for converting impedance data into a distribution of time constants using DRT. The Nyquist plot, the distribution of time constants related to this Nyquist plot. What is time constant? Time constant in an RC circuit is the product of the resistance and the capacitance and is a criterion of the speed of capacitor charging. R times C, charging current, time, charge on capacitor, decreasing of the current. In physics and engineering, the time constant, usually denoted by the Greek letter tau, is the parameter characterizing the response to a step input of a first-order linear time invariant LTI system. The time constant tau is a key characteristic of a first-order linear time invariant system, representing how quickly the system responds to the changes in input. It indicates the rate of change of the system's output in response to a step input. A small time constant indicates that a capacitor charges quickly when a voltage is applied. Resistor, capacitor, and inductor are the topics of the video number E25, Chapter 8, Section 2. Bode and Bode-Phase plots. Bode plots are graphical representations used to analyze the frequency response of linear time invariant systems. They consist of two plots: the Bode magnitude plot, which displays the gain or magnitude of the system versus frequency on a logarithmic scale, and the Bode-Phase plot, which shows the phase shift introduced by the system, also plotted against frequency, impedance magnitude, frequency, delta, that is the phase angle. These plots help in understanding how the system behaves over a range of frequency, especially regarding stability and resonance. Challenge number 27. Thank you for your time and attention. If you like to challenge yourself, please answer these questions in the comments below. 1. Describe the experimental procedures employed in collecting electrochemical impedance spectroscopy data. 2. Is the circuit shown in the previous slide number 384 a type of Randles cell? 3. What's the relation between dynamic response theory and distribution of relaxation time method, both of which are represented by the abbreviation DRT in EIS.